So, in our last module, we have discussed different applications in the field of large sample statistics, and we have discussed that large sample inference or large sample statistical procedures and real analysis and probability theory are just counterparts. So, we can find applications of real analysis and probability theory in large sample theory. So, before we go to the details of large sample theory, we must give some preliminary ideas of mathematical analysis which will be required for fruitful development. So, in this module we shall discuss some preliminary mathematical concepts. Basically, we shall discuss sequence and their convergences and their application in large sample. So, in this module we shall discuss concepts of convergence of numerical series, give some examples and enumerate their application in the field of statistics. So, it is already discussed that large sample inference is attached with the performance evaluation when sample size becomes large. Naturally, large sample methods require the concepts of mathematical and stochastic convergence. Thus, study of asymptotic properties in statistics depends heavily on results and concepts from real analysis and calculus. So, we start with a review of the basic mathematical tools starting from sequence and series. So, we start with sequence of real numbers. A sequence is a function from n, the set of natural numbers or the set of positive integers to the real line R. Thus, a sequence is a set of real numbers given by a n where n is greater than or equal to 1 such that we get a value of n in the real line. Thus, for every n belonging to capital N, we get a value of a n or the value of sequence belonging to the real line. Naturally, the domain in this case is countable and the range is a whole real line. A sequence is thought to be generated sequentially for increasing values of n. As an example, one can thought of 1 by n square or sin n or minus 1 to the power n. So, consider 1 by n square. Then we have the values a1 equal to 1, a2 equal to 1 by 4, a3 equal to 1 by 8 and so on. Thus, we find that the value of an decreases with n. As another example, if we consider n, we find that the value increases with n. However, for minus 1 to the power n, we get the sequence, we get that the sequence is either plus 1 or minus 1. That is, the sequence oscillates between minus 1 and plus 1. Thus, we find that sequences may be increasing or decreasing or bounded. So, here is a plot of increasing and decreasing sequences. So for example, we have taken square root of n as a sequence and we find we calculate the value of a n for different values of n, and quite naturally we get the curve as that of a increasing curve, and in addition we have also taken another sequence which is twice plus e to the power minus n. Naturally, this sequence decreases starting from a value which is higher than 2, then approaches the value 2, or in particular it decreases to a value 2 for large n. Now, one can see the picture of an oscillating sequence. For example, we have in the first plot we have considered sin n, and we find that we get series of values which are between minus 1 and plus 1, but no specific pattern is observed for the sequence. As another example, we have considered minus 1 to the power n, which oscillates between minus 1 and plus 1, but they are neither increasing nor decreasing. So, this leads to the concept of monotonic sequences. Suppose n is a given sequence, then it is monotonically increasing if a n plus 1 greater than equal to an for every possible value of n. Similarly, a sequence is monotonically decreasing if an plus 1 less than equal to an for every n. In either case, the sequence is called monotonic. That is, by a monotonic sequence, we mean either an increasing sequence or a decreasing sequence. It is easy to observe that n, square root of n, e to the power n, or n square are examples of increasing sequences, whereas 1 by n square, 1 by square root of n plus 1, e to the power minus n are the examples of decreasing sequences. Next, we introduce the concept of bounded sequences. A sequence an is said to be bounded if there exists constants k1 and k2 such that k1 less than equal to an less than equal to k2 for every possible value of n, where it should be mentioned that k1 and k2 are independent of n. Since k1 less than equal to an less than equal to k2 implies minus of modulus of k1 minus modulus of k2 less than equal to an less than equal to modulus of k1 plus modulus of k2, we get that modulus of an less than equal to k for some k whenever k1 less than equal to an less than equal to k2 is satisfied. Thus, boundedness of a sequence implies that modulus of an less than equal to k for some k. That is, boundedness implies uniform bound. For example, we have minus 1 to the power n and sin n, and it is quite obvious from our foregoing discussion that minus 1 to the power n is bounded between minus 1 and plus 1, and the same can be said about sin n, which is also bounded between minus 1 and plus 1. Next, we introduce the concept of subsequence. Suppose an is a sequence of real numbers and kn is an increasing sequence of positive integers, that is kn plus 1 greater than equal to kn for all n. Then the new sequence akn is called a subsequence of an. For example, consider a sequence an equal to 1 by n and consider kn equal to twice n. Then the corresponding subsequence is denoted by 1 by twice n greater than equal to 1. Now, if we consider another sequence minus 1 to the power n and take kn as twice n, then the corresponding subsequence is a constant sequence containing only 1. In a similar way, if we take kn as twice n plus 1, in this case we get another constant sequence which contains only minus 1. Next, we shall introduce the concept of convergence of a sequence. Just before going to the formal definition, let us consider some illustrative examples. Consider two sequences 1 by n square and sin n by n. The plot in the next page gives the behavior of these sequences separately as we increase n. Now consider the first plot. We find that 1 by n square, since 1 by n square is a decreasing sequence, it decreases and decreases up to 0. And in case of sin n by n, we find that initially it oscillates and then becomes stable for large n. So we observe that each of the curve decreases with increase in n. Finally, after a large value of n, the curve of 1 by n square becomes very close to the 0 mark. However, for the second sequence, the curve wastes first few n to become stable. But as earlier, the curve maintains a little distance with the 0 value for large n. Thus, in each case, the value of the sequence becomes very close to a postulated value 0. In fact, this 0 is postulated for the given examples. It might not be possible that for other sequences we get the postulated value as 0. In each case, the value of the sequence becomes very close to a postulated value as we exceed a large value of n. This gives the basis to define the convergence of a sequence. So now we shall give the formal definition of a convergent sequence. A sequence AN is said to be convergent if there exists a real constant A such that for every epsilon greater than 0 there exists a positive integer nu. Obviously this nu is a function of epsilon, for which the distance between AN and A is less than epsilon. That is, mathematically absolute value of AN minus A is less than epsilon, and this has to be satisfied for every n greater than or equal to nu. If such an A, the real constant, exists, we write limit of n as A and define A as a limit of the sequence. So convergence of a sequence has two components. Number one, a postulated value or postulated real constant A, and then finding a positive integer nu for every possible choice of positive epsilon. So let us explain the notion of convergence through some illustrations. Consider example 1, where we have considered the sequence 1 plus e to the power minus n. Naturally, this is a decreasing sequence, and by inspection we find that as we increase n, e to the power minus n decreases up to 0. So we just identify the real constant A as 1. Thus, if a feasible nu epsilon exists for every epsilon greater than 0, then we can say that limit of n equal to 1. For epsilon greater than or equal to 1, we note that the distance between an and 1 less than epsilon is satisfied for every n greater than or equal to 1, because e to the power minus n is a quantity which is less than or equal to 1. So if we take some epsilon exceeding 1, this inequality is always satisfied. However, if 0 less than epsilon less than 1, then absolute value of the sequence, the absolute value of the 1 plus e to the power minus n minus 1 less than epsilon gives n greater than or equal to box of minus log epsilon plus 1. Now note that this box means the greatest integer contained in minus log epsilon, and it is interesting to note that since epsilon belongs to 0 and 1, this minus of log epsilon is actually positive. So we get a positive integer nu epsilon, which is minus of which is the box of minus log epsilon plus 1 in this case, and therefore since for every epsilon greater than 0 we get a feasible choice, we find that limit of n exists and is equal to 1. Consider the second example, where the sequence is 1 by n, which is again a decreasing sequence, and by inspection we identify A as 0. Thus, if a feasible nu epsilon exists for every epsilon greater than 0, then limit of n equal to 0. If epsilon greater than or equal to 1, we find that absolute value of 1 by n minus 0 less than or equal to epsilon is satisfied for every n greater than or equal to 1 as earlier, because 1 by n is always less than or equal to 1. However, for 0 less than epsilon less than 1, the same inequality gives n greater than or equal to box of 1 by epsilon plus 1. Thus, we can set our nu epsilon as box of 1 by epsilon plus 1. Since for every epsilon greater than 0, we get a feasible choice, a limit of n exists and equal to 0. Consider our third example, which is defined as square root of n plus 1 minus square root of n. Simply rationalizing, we get n as 1 by square root of n plus square root of n plus 1, and it is easy to observe that this an is nothing but a decreasing sequence. Thus, by inspection we identify A as 0. Now, 1 by square root of n plus square root of n plus 1 is less than 1 by square root of n, and hence absolute value of n minus 0 less than epsilon will be satisfied if absolute value of 1 by square root of n minus 0 less than epsilon is satisfied. Now the last inequality, that is absolute value of 1 by square root of n minus 0 less than epsilon, gives n greater than equal to 1 by epsilon square, box of 1 by epsilon square plus 1. The last inequality gives n greater than equal to 1 by epsilon, box of 1 by epsilon square plus 1 whenever epsilon less than 1, and for epsilon greater than equal to 1 the inequality is satisfied for every n greater than equal to 1. Thus we can set our new epsilon as a box of 1 by epsilon square plus 1. Again, for every possible choice of epsilon, positive epsilon, we get a feasible choice, and therefore limit of a n equal to 0. Next, we shall introduce the concept of a divergent sequence. From the analogy, if a sequence is not convergent, it is divergent. So let us consider some examples. Consider two sequences n square and minus of log n. We have plotted these sequences against different values of n, and they are given in the next page. First, consider the behavior of the sequence n square. We find that as we increase n, the n square becomes larger and larger, and we get an increasing function. And however, for minus of log n, we observe that this minus of log n is a decreasing function and decreases to very large quantity in magnitude as we increase n. So we find that a n equal to n square increases enormously, whereas a n equal to minus of log n decreases as we increase n. Naturally, we can observe any finite number to which a n converges. Naturally, we can't observe any finite number to which a n converges. In fact, after a large value of n, a n becomes infinitely large or small. This gives the idea of the converse of the convergence, that is a divergence. A sequence a n diverges to plus infinity if for any capital M, a positive quantity, there exists a nu which is a function of capital M such that a n greater than m for all n greater than equal to nu m is satisfied. On the other hand, a n diverges to minus infinity if minus a n, the new sequence, diverges to plus infinity. So a sequence either can diverge to plus infinity or can diverge to minus infinity, and we shall discuss only divergence to plus infinity, because divergence to minus infinity is just a simple task using the definition of divergence to plus infinity. So let us consider some examples. Consider our first example where the sequence is a n equal to n square, then a n greater than m implies n greater than equal to box of square root of m plus 1. Thus, setting nu m as box of square root of m plus 1, we get that n square diverges to plus infinity. Note that minus 1 to the power n is also an example of a convergent is also an example of a divergent sequence, as it does not converge to a fixed value but oscillates between minus 1 and plus 1. However, there is a controversy of defining an oscillatory sequence as divergent, but we are just classifying sequences as either convergent or divergent. So if a sequence has a finite limit, we say that the sequence is convergent, and if the sequence doesn't have any finite limit, we say that the sequence is divergent. So let us discuss a few results, regarding convergence of sequences. First one is a convergent sequence is always bounded. Second one is a limit of a convergent sequence is unique. A sequence is convergent if and only if every subsequence from it is convergent. A monotone sequence is convergent if and only if it is bounded. This is a well-known monotone convergence theorem of sequence, and there are some other relations, like if a sequence exceeds b, some constant for every n, then if limit exists, then the limit of n must also exceed this b. And next we have celebrated Stirling's approximation to n factorial, which states that n factorial can be approximated by square root of twice pi multiplied by e to the power minus n, whole thing multiplied by n to the power n plus half. And lastly we have exponential approximation, which states that limit of 1 plus c by n whole to the power n equal to e to the power c for fixed c belonging to real line. So let us give some applications in large sample theory. In example 1, suppose x has a Poisson distribution with mean 5, and we are interested in probability x equal to n for a large n. Observe that for n greater than 5, 5 to the power n by n factorial is less than 5 to the power 5 by 5 factorial, or in some sense for n greater than 5 we find that 5 to the power n by n factorial is bounded by some sequence which has limit 0. Therefore, limit of 5 to the power n by n factorial equal to 0, and hence we get that limit of probability x equal to n equal to 0. Thus, for large n the probability is negligibly small. Let us compute probability x equal to n for different values of n. For example, if we take n equal to 20, we get probability x equal to n as 2.64 multiplied by 10 to the power minus 7. If n is taken as 30, we get another quantity which is 2.36 multiplied by 10 to the power minus 14. That is, as we increase n, we get that decreasing values of probability x equal to n, and for n equal to 40 we get 7.5 multiplied by 10 to the power minus 23, that is almost 0. So it is easy to observe that the limiting value of 0 is reached for n exceeding 30. So we have just seen how sequences are necessary in evaluating large sample performances in statistics, but there are some other mathematical tools which are known as series and their convergences. So in our next module we shall discuss series, their convergences, and some properties and how to check convergences of a given series in details, and enumerate their applications in statistics, or particularly in large sample statistics.